Welcome to the first video in the presentation regarding Buffon's needle problem. This question was originally posed in the 1700s by French naturalist Buffon, and it asks, what is the probability that if we drop a handful of needles onto a wooden plank floor, what is the probability that a single needle will lie across one of the dividing lines? So in this case, I have 10 needles and I am just going to drag them onto here. And I'd like to make note of the fact that in the statement problem, the needles do need to be of uniform length. So this representation may be slightly off because the needles may lose a little bit of length while being adjusted for different orientations. But in the original question, obviously, the needles are of uniform length, and we just throw them onto this wooden plank floor. I am dragging these up here in no particular order or particular placement. So this is what it could look like theoretically if we were to drop these needles, right? So if we look at how many cross a line, we have 1, 2, 3, 4, 5. So we have 5 out of 10 of them crossing one of these lines. And again, these were randomly placed. So our experimental probability that a single needle crosses one of these lines between the planks of wood is 50%. Okay. So that is a very crude example of this question where I am only using just a few needles to get the idea across. And one other thing that I'd like to note is that each of these needles will have a length of L. And in this case, we will assume that this distance here is also L. And when I'm working with this question, whether it's providing a real life example or an illustration, the distance between any of the two horizontal lines will always be at least the distance or the length L of the needles. I will be using toothpicks in my example, but the idea is still the same. So again, this is just a very basic example and introduction to the concept. It just looks at, given that we have this wooden plank floor and needles in our hand, where in this case, the distance between the planks is just the same as the length of the needle. What is the probability that a single needle will be crossing one of these lines? And in this random experiment, we got 50%. We will see that this value actually does not accurately represent the theoretical probability. We will be using calculus to talk about the theoretical probability, also with a mix of statistics to get the actual value. And what we will see is that when we find the theoretical probability, it is actually expressed in terms of pi. So we can use this experiment as a Monte Carlo method to get an approximation for pi. And you guys will see that later in the video when we get our theoretical probability. So this is just a very brief introduction. I will now move on to the next portion, which is a real life example. I will be dropping 135 toothpicks onto a chalkboard, and then we will do the experiment like that. So I will see you in the next video. This is just a brief introduction. Welcome to the second video in this presentation. I am going to be talking about the experiment that I actually did for the needle problem. I'm not going to go into all the details because I made it very clear in the first part. So let me just get started. So I have 2 toothpicks lined up tip to tip on this chalkboard, and I assign them a length of L. And just for reference, they had a real length or measured length of 2.5 inches. So there is 5 inches between each of these pairs of lines, again, acting as our planks. So 5 inches apart, and a toothpick has a length of 2.5 inches. This is the setup on a chalkboard that I simply put on the ground, and then I dropped my needles on it, which we will see in the next part here. So in the next part, this is the toothpicks or needles dropped on to the chalkboard. As you can see, they were randomly dropped. They do not have any type of alignment or order to them. I dropped 134 of these toothpicks onto my chalkboard, and just as a little side note, it was 134 because I had to throw one of my toothpicks out because its length was not consistent with all the others. Anyways, this is what the board looked like after I threw my toothpicks on to it. So what I then did was sat down and counted how many toothpicks crossed the line like we discussed. So I counted them and took them off of the board as I did so. And after I did that, I had my number of toothpicks that crossed the lines, which is exactly what we needed to look at. So the next scan is what the board looked like after those toothpicks that were crossing had been moved. Now, I do want to note too that some of these may appear to be touching in the picture, but that's because I accidentally knocked a couple of them when I went to pick up the others, but the official count was 46 toothpicks that were touching. So we have our planks, we have our quote unquote needles, and we had that 46 out of 134 of them were touching the lines. And that's all that this last scan shows. So 46 out of 134 were lying on one of the dividing lines or spaces in the quote unquote planks. So this number models the probability that a randomly selected toothpick is lying on one of the lines, right? So our experimental probability of a toothpick lying on the line or a line was 46 out of 134, which is roughly a third. So this result that we got is actually very close to the theoretical value that we will see in the last part of this presentation. In fact, it was only off by a couple hundredths when calculated correctly. So the approximation that I did worked well, and it's an idea that again ties back to the Monte Carlo samplings that we saw, because I did the very crude example at first with just 10 toothpicks and saw that we got 50%, right? Which is not very close to the theoretical value. So we see again that in this case, I'm using 13.4 times the amount of toothpicks, or 13.4 times the original sample size, right? So we're getting more and more elements in our sample, and we see that we actually do tend closer to the mentioned theoretical value. So that is, like I said in the first part, and again here, that's how this kind of ties into a Monte Carlo method, because we are increasing our sample size, and in doing so, we see that we reach or get closer to the theoretical value that we arrive to by using mathematical definitions and formulas. So that's just an important note to make. And again, we will see that the theoretical value or the theoretical probability actually involves pi, which is, like I mentioned in the previous video, something that we can approximate using this as a kind of Monte Carlo method. So I won't talk about this section anymore. We'll go ahead and get straight into the theoretical mathematics that back this question up. Welcome to the final video in this presentation about Buffon's needle problem. In this video, I will be going over the theoretical calculations that back up the probability that we calculate within this question, right? So recall that the basic question has to do with planks of wood and needles, and it just asks if we have planks of wood and we throw needles onto these planks of wood, what is the probability that a single needle will be crossing one of the horizontal lines? So in the illustration that I've provided, we have that the wood is spaced apart at the same distance as the length of the needle. So the length of the needle is L, and I'm saying that these planks have a width of L. Now, this distance, capital D, in this case, it is equal to L, but I am just using this to denote the distance or the width of the plank. And with the proof that I will present today, it will work, the method that is, will work if the wooden planks have a width that is greater than or equal to the length of the needle. So if that is not true, then this method for calculating the theoretical probability will change, and we would have to do a different method. But for the original statement of the problem and for its variations, we work under the assumption that we are at least L units wide for each plank. So here's our picture. I will erase this because we don't need that fact for our proof. It's just something that I wanted to point out. But here is what we have. So we have our plank of width L. Here's our needle. And now I am going to just drop another quote unquote needle like this. So here is our needle. This is a random needle. There is nothing particular about this. It does not have to be at this exact orientation or position. This is just a random needle that is dropped. So what are we going to be looking at for this needle? Well, we're going to be looking at from the center, which is what I have marked, what is the vertical distance from the center to the nearest line? Well, this we will call lowercase d, right? So lowercase d is the vertical distance between the closest horizontal line and the center of the needle. And then from there, we will also be using the angle theta that forms between the horizontal line, which is located at the center of the needle and it's parallel to the other horizontal line. So we will be using this angle theta, and it's just the acute angle that forms between this imaginary horizontal line and the needle, right? And a couple things to note. So this distance d will be between 0 and L over 2. So this distance, lowercase d, will be between 0 and L over 2. And that's because the quote unquote best case scenario is that when the distance d is 0, then that means the center of the needle is lying on one of the horizontal lines. And the quote unquote worst case would be in a case like this, where we drop the needle and its center is halfway between this length. So the closest line, they are both equally as close, and the length from the center to either one is just L over 2. So d ranges between these two values, and then theta will range between 0 and pi. So we have that theta is between 0 and pi. And the reason that that is because if we were to just drop needles, right, arbitrary needles, if we have a needle like this, our theta would measure from the horizontal to this point here. Let's say we drop another needle and it ends up going a little bit farther. So we have another needle that kind of swoops a little bit more and ends up like this. Well, instead of measuring the angle from the horizontal all the way around, we will just circle back and look at this theta here. So regardless of how we drop the needle, we will just range our theta from 0 to pi, because once we get past the threshold of landing on top of this horizontal line, we can just start measuring the angle it forms here again. So this is where our values for d and theta are bounded. And with that, we can actually draw a graph to visualize and understand a little bit more what is going on. So I will make my vertical axis the d axis, and I will make this the theta axis. So we have d as the vertical axis, theta as the horizontal axis. And with that, we will just plot what we know to be true. Well, what do we know? We know that d is strictly between 0 and L over 2. So here is L over 2. And then this is our 0 value. And then we know that theta goes up to pi, right? So we will put pi here. So we know that these two values will range from 0 to L over 2 for d, and then 0 to pi for theta. Okay. And these variables both follow a uniform distribution, because all of the values for d that rest in between 0 and L over 2 are equiprobable. So there is not a single value that is more likely to appear than another, because we're just randomly dropping the needle. The same concept holds for our theta. So representing that on this graph, we have that we get a rectangle for our values, because these are, again, uniform distributions. And when we kind of plot both of these on a single graph, we will get this. And an easy way to understand this is by looking at, if we were to drop a single needle and look at the value d and the value theta and combine them into an ordered pair, right, where we have theta comma d. So it's like x and y. Theta is on our x-axis, d is on the y-axis. Once we plot this ordered pair, it will be somewhere within this rectangle, right? Because we know that d is bounded by, or is contained within, these values, and theta is contained between these values. So anytime we drop a needle and measure theta and d and plot those coordinates, or plot them as a coordinate within this graph, it will end up within here. So this is actually our entire sample space when we are considering dropping needles, right? This is any needle we drop, its measurements or characteristics, however you'd like to conceptualize it, will lie within this rectangle. So this is our total sample space. Now, the important part, or the big logical reasoning, has to do with, when will a needle cross one of these lines? Well, the needle will cross when its vertical distance, right, when d is less than that vertical distance. And drawing another picture will be helpful. So let me clear some of this stuff out of the way and amplify it just a little bit. So if we have our needle like this, right, and we go to about where the center is, remember d is going to be from here to here. It's just the vertical distance from the closest line to the center. So this is d. And then, so a needle will cross when that distance d is smaller than this distance, the vertical distance from the center of the needle to the tip of the needle. Because if d is less than that, then we will be intersecting. It can be equal to it, because if the tip of this needle is touching, then the vertical distance d to the center, right, from the center of the needle to the closest line will be equal to this vertical distance. The vertical distance from the tip of the needle to the center of the needle. And we can actually find that out, what that value is. So again, the needle will touch if D is less than or equal to that vertical distance. Well, what is that vertical distance? Well, this is L over 2 because our needle is of length L. And this from the midpoint to that other end will just be half of L. And then we have our theta here, right? So we would get that the sine of this theta, I will call this vertical distance V. And remember, this V is the vertical distance from the center of the needle to the tip of the needle. So we can solve for V, right? So sine of theta would be V over L over 2. So that vertical distance ends up being L over 2 times sine of theta, right? So D, when D is less than or equal to that value, we have that our needle will be crossing a line. And we can actually plot this. So this, since this is a trig function scaled by a factor, right, it will end up looking like this. So that is this function here, and I'll just call it F. So that is this function F, and we need to figure out all the D values for which this holds. Well, all the D values for which this inequality holds is just the area under this curve, right? So if we find the area under this curve, we are finding how many D values satisfy this inequality, which we can also think of as the number of ways that our needle will touch, right? We just need to integrate this to find out which D values satisfy this condition. And again, this condition guarantees that a needle will be crossing one of the horizontal lines. It is an if and only if. So we can use calculus to figure this value out, right? And to do that, it's very simple. We will integrate from 0 to pi our function L over 2 sine theta, right? So L over 2 sine theta from 0 to pi, and then we will be with respect to theta. So once we integrate this, that will be negative cosine, negative L over 2 cosine theta, right? And then once we evaluate that from 0 to pi, we will end up getting that the integral of this is just L. So this area here is L, right? And that corresponds to, again, this condition being satisfied, right? So the condition that this is satisfied guarantees that a needle is crossing. So we have that this area is L. And now if we want to find the probability of a needle crossing, which that will just be event E. So the probability of event E, where E is the event that a needle is crossing one of the horizontal lines. Well, we'll take the number of ways that can happen and then divide it by the total number of outcomes, which is our sample space. And then speaking geometrically, what that corresponds to is taking the area of the integral that we got and then dividing by the area of our total sample space, because that models the number of ways, or kind of the volume of ways that a needle will cross over the total number of ways, or the volume, if that's how you'd like to conceptualize it, area that we just have in our entire sample space. So we have L divided by, the height is L over 2. So the area of the rectangle is easy. It's just L over 2 times pi. And then what we get when we do that is actually 2 divided by pi. So 2 divided by pi, right, is the probability that a needle crosses a horizontal line, given that the spacing or the width of the wooden plank is equal to the length of the needle, right? So this is the answer to the question. The probability for the needle problem first posed by Buffon is 2 divided by pi. And what we can see from that is, so the theoretical probability is 2 over pi. So if we have a sample size, right, of capital N, and then we are going to, so if we looked at a sample size of N, and we looked at the number of needles that crossed, which we will just say C for cross. So if we take the number of needles that crossed and divided by the total, it should be approximately 2 divided by pi, which would then tell us, right, that 2n, right, so 2n divided by c should be approximately pi. And this is how we can use the needle problem to approximate pi. And as we increase our sample size n, c will also increase, obviously. And the reason this is an approximation is because it will not be a perfect answer, as we know with Monte Carlo methods, but we know that as we increase our sample size n, that we will get closer and closer to this value. So if we did the needle problem with a bunch of needles, hundreds or thousands of them, and we used this formula, we would actually be able to approximate pi. That is exactly how this ties into the Monte Carlo methods that we talked about in class. So that is how we can figure out the theoretical probability for this question. Again, it just goes back to this simple diagram and then a little bit of integral calculus to figure out the probability. And this is how we can use it to approximate pi by using Monte Carlo methods. So I hope you found this video cool or useful in some way. It's just a very interesting problem to look at, but I appreciate your time and I thank you for watching.